Hello, my name is Reynolds. Welcome to College Algebra Section 6.3. Today I'm going to show you how to graph exponential functions and what exponential functions are. So the first thing you need to know is all exponential functions start at 0a, and the general equation of an exponential function is a times b, x minus c is the horizontal shift plus d is the vertical shift. So I'm looking at this one, many students would think that the a term or the start value would be a 2, but if you were to rewrite this, this is actually 1 times 2, and 2 is actually the b or the base value of this. There is no c shift and there is no d shift. So this a value starts at 0, 1. From there, we're not going to shove it left or right or up or down, so I'll just close that dot. The asymptote is always at y equals d for exponential functions, and there are 3 things that cause decay. We're going to look for decay indicators if we have a negative x, a negative a, and a b value between 0 and 1. So there's no decaying factor. So here comes your first look at an exponential function. If you want to find more points, you can plug in for x and solve for y. I don't make a big deal about the difference between this red line the red function and the green function. Keep in mind the base will look different, and that's what this first example is looking at. This looks, in my book, would look almost the same. The asymptote is still at y equals 0. The point is still at 0, 1, and we still have growth because we have no indicators. And again, this isn't maybe necessarily as accurate as you want it to be, because the actual graph might look a little bit steeper since they used a base 4. If you want to plug in extra numbers, you can. I'm not a big fan of the x and y t-chart plugging and chugging. So I'm just looking for some generalities of what these graphs look like. I'm looking for 1 point, I'm looking for an asymptote, and then I'm looking for some growth or decay or the general sketch. But keep in mind the actual graph of 2 to the x does look different than 4 to the x because, well, this one's exponentially increasing faster. So then we have the rules that I gave to you. Always start at 0a, so in this case the a value is not 2, the a value is 1. We have the asymptote always at, I should have written it here, y equals d for my asymptote. You should have that in your notes as well. There's no decaying factors here, so I would give me some growth. There are basically 4 basic graphs. I'm going to show all 4 of them to you. Here the value of a is actually negative 1, and I can write it so you can see it. If I put it in this general standard graphing form, the value of a is negative 1. So this time I'm going to start down here. Again, I'm not moving it left or right or up or down, so I'll actually close that dot. The asymptote's still at 0. But this time, because we have a negative a, we're going to have some decay. And just incidentally, if you had 2 decaying factors, in this case we just have 1 decaying factor. But if you had a negative x, a second decaying factor, or if you had a b value, a base, in this case the base is 2. But if you had a base between 0 and 1, or a fractional base between 0 and 1, that would cause a second decaying factor, and 2 decays would cause growth. I only have 1 decaying factor, so I'm going to decay, and it's kind of like 2 negatives form a positive. 2 decaying factors would be growth, back to growth. So looking at these last 2 examples, again, the value of a is 1, so I'll start at 0, 1. I'll close it because there's no c or d shift. The asymptote's at y equals 0 because there is no d shift. And because of the negative x, I'm going to have decay. So this graph looks a little bit different than the previous graphs because they're both starting at 0, 1. This graph here starts at 0, 1, and this graph starts at 0, 1, but this has growth and this has decay. The last graph is your example of 2 decaying factors. This time I'm going to start at negative 1. Asymptote still at y equals 0, so there's the negative 1. Y equals negative 1 times 2 to the negative x, pardon me, plus 0. So again, the asymptote's at y equals 0. That's that vertical shift. It's not being shifted. This dot's going to be closed. There's no horizontal shift or vertical shift here. And again, as I mentioned earlier, because I have 2 decaying factors, a negative a and a negative x, this would be growth, which I think is the final 4th scenario that I could have for exponential functions. So again, this one's, I start at 0, 1. have the asymptote at y equals 0, and this is going to be decay. This looks just the same in my book. Of course, realize that these two graphs are actually a little bit different because this has a base of 2, this has a base of 4. So this one might be decaying a little bit faster, where this one starts out. But look, the ending graph looks the same. I still have y equals 0, and they both have that dot at 0, 1. So again, I'm looking for a dot, an asymptote, and then a swoop. And either it's a growth swoop or a decay swoop. I'm going to introduce the value of E here as well. E is approximately 2.71828. And it's kind of like a value of pi. So again, that's the base. As long as the base is not a value between 0 and 1, it's going to be growth. So I don't see any decaying factors here. The value of A is 2, so my start value would be here at 0, 2. So I always start at 0A. I have no horizontal shift, no vertical shift. In fact, my asymptote's at y equals d. And there's nothing that causes decay here, so I would go through the point 0, 2 and give growth. This one, I start at 1/2, because that's the A value. The asymptote's at y equals 0 because of the d shift. And because of the negative x, it's going to be decay. Now keep in mind that negative 0.58 is going to cause that thing to maybe look a little bit different. But again, I don't know if it's graph A or graph B, but I'm not concerned. We're just doing some quick sketches. I need an asymptote, a point, and a swoop. Here are the actual graphs. You can pull out your graphing calculator. You can see the book emphasizes finding more and more points. I'm not going to hold you to be that accurate. So make sure you can type these things into your calculator. 2 caret up, 1.4 to your graphing calculators. Here are just some rules. You should know x to the third times x squared is x to the fifth. And you should know x squared cubed is x to the sixth. Here's a rule that sometimes students forget. X to the negative first is 1 over x. So if I give you 5 to the negative first, that's equivalent to 1/5. And the last one, anything to the 0 power equals 1. So make sure you understand your exponential rules that keep coming up. And then here are your rules for graphing, which I would have down in your notes and memorize for your test. Again, the book's going to emphasize that you make a quick little t-chart, plug in for x and solve for y. Not a big fan of that, so they teach it a little bit differently. Exponential graphs and functions, I'll kind of slide through these. Again, I'm not encouraging you to find all this, but you can see 2 to the negative second, that's why they introduced these exponents. They want you to know that this is 1 over 2 squared, and this is 1 over 2 cubed, which gives me that 1/8. So it's important if you're going to locate those points to be able to evaluate those. Remember, 3 to the x in my book looks just like 6 to the x. Actually, in reality, it's not, but the asymptote's the same, the point's the same, and the swoop is going to be the same in my book, but realize that they do look a little bit different. I won't count off on your tests if you just have the point, the asymptote, and the correct swoop here. Since it's a fractional exponent, remember that's going to cause decay. That's not a start value. The start value is a 1. Remember, you don't look at the B value, you look at the A value, and there's the asymptote, that D shift. So again, just some more graphs. I have some examples here for you. This is good. The start value is not 2. The start value, again, is 1 time, so the value of A is 1. This is the first time that you're going to see it shifts 3 units down, so 1, 2, 3. No units left or right. The asymptote's also at y equals -3, and because you have one decaying factor, be careful, this is not a decaying factor. Negative D is not decay. If you have a negative x, that's going to cause decay. And so that's how you quickly graph that function. Again, the book's going to go through stages and have you do transformations. I would just come up with the final graph, get there at the end. This is defining the value of E for you. If you plug in, maybe perhaps you remember this PERT formula, principal 1 plus r over n to the nt. Well, if you push this to the limit, which is kind of a calculus term, this number, as you keep increasing n, gets closer and closer to that value of E, which is that 2.71828, mostly used in compounding interest. And so they're going to say, hey, E is, as you push this to the limit, and that's what this infinity is, as n gets really large, it's going to approach. And here comes some values they're going to show you. Hey, look, this number never gets past 2.7, I call this the Andrew Jackson number because he was our 7th president elected in the year 1828 for 2 terms. 1820, this should be an 8. That's interesting. Yeah, I think that should be an 8. But at any rate, so they're evaluating the E. For our purposes, E doesn't matter. E looks just like, my graphs would look just the same. Doesn't matter if I have a base E or a base 2, because as long as I don't have a fractional exponent, we start at 0, 1. We've got the asymptote, and we have growth. Again, the value of A here is -1. I'm going to put an open dot at -1. I'm going to shove it 3 units to the right. How's come? Because I'm going to try to set this equal to 0 and see that x does equal 3. So this actually goes 3 units to the right. I'm not going to go through the open dot. I'm actually just going to go through that closed dot. The asymptote's at 0. And because I have one decaying factor, which is the -a, remember, this is a -c, so that does not cause decay, but I have one decaying factor. It's the -a value. I would have decay, so I'm going to start up high and head down low. So the majority of this exponential is about graphing, but there are some problems that you're going to be held responsible for finding like bases and solving for exponents. So 2 to the 3 minus 1 is equal to 2 to the some power. My recommendation would be do some upside down division. I'm not a big fan of factor trees because they kind of look messy. 16 times 2, sometimes you go 4 times 4, and then, and then 2 times 2, and 2 to, I just hate these factor trees because you might lose this little factor here and forget it's actually 2 to the 5th. This looks a little bit more organized for me. Take half, take prime numbers. 2 goes into 8 4 times, 2 goes into 4 twice, and then you can see 2 to the 5th is how you can rewrite 32. So I call this upside down division. It's a little bit faster, a little bit neater to organize your thoughts. So the process here is if 2 equals 2, if the bases are equal, the only way for these this equation to be equal is to set our exponents equal to each other. So the only time that the left side is going to equal the right side is if 3x minus 1 does equal 5, or 3x equals 6, or x equals 2. So the goal there is to try to go for some like bases. We'll get to graphing just a little bit more. Again, the like base here, I choose a prime base, 3, so this is 3 squared. So I'm going to set 2 equal to x plus 1 because the bases are equal. So I'm going to set the exponents equal. So 2 is equal to x plus 1, therefore x equals 1. Down here, remember our exponents rules. I'd use 2 to the negative first is actually the same thing as my 1/2. So I'd rewrite 1/2 to be 2 to the negative first, and I'd rewrite 8 to be 2 cubed. Continue to simplify using my power raised to a power rule. This is 2 to the negative x is 2 cubed. So negative x is 3, or x is -3. You can actually go back and type this into your calculator and actually punch this in. 1/2 to the -3 better be 8 because the negative does the reciprocal of it, and we know 2 cubed to be 8, so that actually does check. You can do that in your calculator as well. So I have a little worksheet or a handout. If anyone's interested in a blank copy, email me and I'll shoot you a blank copy so you can practice it. But I'll go through a couple more graphs and then we'll end this video. This is a start value at -3. I'm going to shove it 2 units to the right, 1 unit up to find my closed dot. There's that one strong dot I need. The asymptote's at y equals 1, and I only have one decaying factor, so I would give me some decay for this. And there's the actual answer for this. Let's try this again. I have a start value at 0, 3. I put an open dot there. I'd go 2 units to the left, 5 units down, 3, 4, 5. Remember, you always go the opposite direction when you see those parentheses. And some students say, well, you don't really see parentheses, but in order to type this in the calculator, you would, because you'd have to go 1/4, caret up, x plus 2, close the parentheses. So you do have parentheses if you type it into the calculator. So again, this would say, when does x plus 2 equal 0 when x is equal to -2, and that's why it's going 2 units to the left. This says 5 units down, but it's also my D shift, and that's where the asymptote's at. So 1, 2, 3, 4, 5, we'll put the asymptote at y equals -5, and because I only have one decaying factor, which is the b value between 0 and 1, this is also going to be some decay. And the final answer should look like this. Continuing on, the value of a is -1. That's an open dot. I'm going to move it. This is going to be 2 units to the right because 2 minus x is equal to 0 when x equals 2. It's a positive 2, so go right and 3 up. So 1, 2, 3, boom. This says 3 up, and it also tells me where the asymptote's at. Y equals 3. And let's see, we're going to have 2 decaying factors. So I got a -a, and I have a b value. Oh, I have 3. Holy cow. 3 decaying factors would be back to decay. So start up high and head down low for decay. Yep, there's the answer for that graph. For this one, I would start at -1. I would shift it just 1 unit up. And it looks like the asymptote would be at +1, and I have 1 decaying factor. And the final solution should look like this. For this one, I would start at 1 because the value of a is 1. I've got a b value, so that's going to cause decay. I would go 3 units to the left, and the asymptote's at y equals 0. And there's the graph for that. Finishing up here, I've got a start value at 2. I would go 4 units to the right, 1, 2, 3, 4, and 1 unit down. I would have the asymptote at y equals -1, and I would look for any decaying factors. I don't see any. So I would have this as growth. Growth means start low. You read a graph like you read a book from left to right. So start low and head high. And so I'll just show you the rest of these if you want. Oh, this is interesting. When does 3x minus 6 equal 0? Because I'm setting that equal to 0. So 3x minus 6 equals 0 when x equals 2, and that means go 2 to the right. So my start value is at open dot 0, 3. It's always, you always start at 0a. That's a start value. So I'm going to move that open dot 2 units to the right and 4 units down. 1, 2, 3, 4. The asymptote's at y equals -4 because of the d shift. And it looks like I have just 1 decaying factor, a b value between 0 and 1. So I know that's going to be decay. Start up high and head down low. And again, that might not be the actual graph. The actual graph might look something more like this. Just make sure that you go through that 1 dot that I'm looking for. Give me the asymptote. It's nice if you write the equation of the asymptote, in this case y equals -4, and I'm just looking for some decay factor. If you want to find more points, you certainly can. There's number 8. Remember, the -x is going to cause decay, and this causes decay, so that's going to be a growth. And number 9, and the video is going long, so multiple choice. If you have questions, email me.